Yes? Okay. So I'm giving an hour talk about some of the main core of learning theory, and what I want to do is especially give estimates, which I think are give theory a lot of solidity, and depth. So I want to especially eventually get to stating, at least with some ideas maybe of proof, of some main estimates. So I just want to review things that almost all of you know pretty well. This is what may be called the standard model in learning theory. So the main thing in learning theory is we have data from which to learn. These are xi, yi pairs. And the idea is this data is drawn from some probability distribution, rho, on the product space x cross y. X is some reasonable space. For me, always a topological space. For example, a complete metric space or a subset of a Euclidean space, closed and bounded. Y will just be the real numbers in this talk. And so on this space, x cross y, we have this probability measure, which isn't known. And what we do is try to, from the data, that's the empirical, that's the part that we have at our disposal, we want to find a function which produces y from x in a reasonable sense that will become clearer as we proceed. My own point of view is that rho, the probability measure, is God-given. That is the primary part of the problem that we're discussing, and everything else is man-made, reconstructed by man. For example, kernels. They're very important, but they're not the primary object. They're not what's given to us. And the same for any metrics on our spaces and so on. Sometimes they play a good role, but what is God-given is just the probability measure which produces the data. That's the point of view we take here. All right, then we try to fit this data. The data could be represented by points on the xy space, xy plane for visualization. We try to fit this data by our function f. So we're looking for a function f. Now, there is a canonical function that's produced for us simply by the data. So there's this regression function again. This is a review of things that most of you have seen and maybe know very well. The regression function is given just by averaging y with respect to the conditional measure for a given x. So we want f rho of x, we just average y with respect to that conditional measure. That defines a function f rho from the space x to the space y. And this is the function that we want to learn. As I say, this is defined exactly by rho. No other constructions necessary. So you could say it's derived from the God-given rho, and it has a very primary role to play in that respect. And because averaging is so fundamental to statistics and probability, it's for lots of reasons that we want to learn f rho from the data. Okay. So from the data, we want to produce some function from x to y, which in general will approximate the regression function. This whole talk is from the point of view of regression rather than classification. So for classification problems, oftentimes this point of view will be very helpful and lead to answers, but sometimes it's better to ignore the regression function. But this talk is then in terms of finding a good function rather than finding a classifier. Okay. So we want to find some algorithm. In fact, we'll focus on a very particular algorithm, which gives us a map from x to y. And we want this hypothesis produced by the data, fz, we want that to approximate f rho. That's the goal. You might say it's the goal of learning theory from the perspective of which I'm speaking. Okay, so there are different measures for approximation, but there's the most natural measure is, of course, one that comes only from rho itself, the space, the estimate I've written at the bottom of this page. We say that if this integral is small, then fz is close to f rho. And here we're integrating over rho sub capital X. This is called a marginal measure. Rho induces a natural measure on the space X, just by projecting x cross y onto X. So there's a natural measure on rho X, and with respect, integrate fz minus f rho. These are both functions on X, so all this makes sense, and that is the most natural error. I would say learning theory, and in fact, probably even most of the talks here at these tutorials, they have a different version of error, which sometimes is very close to this and sometimes not. For me, this is really the gold standard for error functions, getting fz close to f rho. There are lots of other ways of looking at errors, and they have their merits. But a lot of them are data dependent, and I prefer a development of the subject which aims less at data dependent quantities, gets estimates in terms of data independent quantities. And of course, fz depends on the data, but otherwise than that, we like to keep the subject as data independent as possible. That's my own point of view, and I think one obtains a deeper understanding of these problems by using estimates which come from this. And I'll try to give some example. Now, there's one algorithm that seems especially fitted for the problem that I've described, this regularized least squares. It's especially tuned towards this regression function, and it's computationally very good, as we'll see. And what it amounts to is we take some space of functions. Many of you aren't happy with Hilbert spaces, I don't think, but think of that as just an inner product with some kind of closure property on the space of functions, on a space of functions from x to y. So you think of this H as a space of functions from x to y. And it has a norm on it, or it has a measure on it defined by some function, by some inner product. Okay, then what we do is we take this regularization parameter lambda. Otherwise, this minimization does not make such good sense because of lacking a unique minima. To get a unique minima, then one optimizes this function I've written towards the bottom for a fixed lambda positive. Lambda generally to be chosen later according to theory or practice. Okay, so this is the optimization problem that we want to solve. Don't hesitate to stop me if I say things too not clearly or for any reason. But so then the algorithm then is this regularized least squares for a function space which I've yet to specify. All right. Now, there is a space that most of you know by now, especially attuned to solving this problem. That is this reproducing kernel Hilbert space. And we'll see, and you've seen already why this is great and beautiful. And I think learning theory has brought this space, this reproducing kernel Hilbert space back into science and mathematics more than anything. The origins go back to the University of Chicago. E.H. Moore in the mathematics department discovered these spaces back in the 1920s. Okay, so here we are. So we start with a Mercer kernel, and I'm demanding that the kernel be continuous. There are lots of reasons for doing that, which I won't pursue at the moment. And I want this to be symmetric, so k of x and t is the same as k of t into x. And there's a positivity condition that's important here. If I take the matrix kxi xj for any finite set of points, x1 up to xl, say, then I want that matrix to be positive semi-definite. This is just a square matrix, symmetric, and the positivity condition is precisely that that be symmetric, that this be semi-definite matrix for any set of x's. Okay, and here I think I better get away from this for the moment. Here are the examples that are the most common, and you can generalize this a little bit by putting a d here. So if you put a positive integer there, you'll get a space of polynomials, homogeneous polynomials. And d equals 1, then you get the linear kernel. And you get an analytic kernel with a second one called the Gaussian kernel. And these are, in some sense, the most elegant, and they're very elegant kernels. And I think for that reason they are the worst kernels. And this is something I'm just beginning to understand more clearly after vaguely thinking about this for some years. And I want to argue that these kernels that are so clean are bad exactly because they're so clean and neat and elegant. Because the corresponding reproducing kernel Hilbert spaces derived from these kernels are filled with functions which are linear or polynomial or C infinity or analytic. And those are the kind of functions that are very hard to approximate the functions that one comes across in learning theory. And so I think, I would guess that these are going to turn out to be less efficient for most problems in learning theory. If one started with a problem and wants to learn like a polynomial, that's fine. But polynomials are not the primary goal of learning theory. These functions, the regression functions, will tend to have bumps. So let me say something about that. Oops, I should put the light on the board. If I want to use the board, I think. Okay. Yeah, thanks a lot. Maybe take off the slide. Well, that's good. Okay, so here's f rho. In general, it will be a function which in classification, something like that, it will be discontinuous or have breaks like this which make it continuous but not differentiable. So these would be a typical f rhos that one would come up in huge number of situations of learning theory. So a kernel that Ming, Na Kwong Ming, has been working out for us in the last days, even today. We had questions posed to him. My work with Andrea Caponetto led to questions connected with Sobolev spaces, which take us into too far a detour. But the thing is, eventually we have this computation, or this new kernel, Sobolev kernel. And it's going to be described k of t, k of x and t. Well, it's just like the Gaussian kernel, except you take off the square. And you can put a constant in here. Let me put this constant in. You can put any constant. It doesn't really matter so much. taken A norm x minus t like this. So we've taken off the square of the Gaussian. And this is motivated by these things called Sobolev spaces that have a huge role in scientific computation, but some use in learning theory, but they're difficult because of using standard measures instead of a measure that we don't know from learning theory. But what we can do is to use this kernel to get a space, which I'll describe presently, the reproducing kernel Hilbert space, defined by this kernel, will be generated by these functions. I forgot a minus sign with A positive. And we know that these functions are continuous but not differentiable. So we're able to see these quite naturally in our spaces. So the approximation estimates, I would conjecture, and I hope we'll have theory to do that before too long, to show that these kernels will be more efficient for problems in learning theory when at least one does not have something like a polynomial for the regression function. That's the idea. But as I say, these are very new yet. I think correct. I mean, I've bothered Ming a lot in the last 2 or 3 days to be sure we have a correct computation there. And this is motivated by the Sobolev spaces, for those of you who know that, where we're taking the index in the Sobolev space to be the dimension plus 1 over 2. This makes the Sobolev space consist of continuous functions but not differentiable functions. And so this is actually, working on Rn, this is actually a Sobolev space of this index. And the kernel turns out to be this miraculously nice, simple object. And the point is that when we have a kernel as this, then we can use it very quickly in the computation. If we have an implicit kernel, it's much tougher. This is an explicit kernel, but it serves to deal with this. But it has especially this feature that it's continuous and not differentiable. And that's the feature, I think, that could help see a great use for this in learning theory. As far as I know, this has never been used in learning theory, although somebody might correct me. Okay. Okay, so, oops. Is that thing okay? Good. So now, as we've anticipated, I want to construct a Hilbert space from a Mercer kernel in general. The Hilbert space will be used in the optimization problem that I spoke of earlier for obtaining a data hypothesis from the data. Okay, by the optimization, we had a Hilbert space of functions. Well, we'll use this particular Hilbert space as defined as follows. We write k sub x of x prime by the kernel, and use the k sub x's to become a basis for the space. So what we do is we take all linear combinations over all possible finite sets of xi. So this is well defined. It's just finite linear combinations of these functions defined by the Mercer kernel. We take all possible sums. That's a vector space, algebraically. And we put an inner product on it by defining the inner product on the basis elements, the kx's by kx x prime equals k of x x prime. And now it can be checked. This is an inner product, a positive inner product, because of the positivity condition we had on the Mercer kernel, symmetry and so on. So this is an inner product, and we just complete that to obtain our Hilbert space HK. Okay, I think you know this. Then we had the optimization problem 3 slides earlier. And the solution exists as unique in general. And in this case, it's easily found by a short, or rather simple at least, computation. It's a problem in linear algebra. So we can write down the solution to the optimization problem. The proof's not very hard. So we have our sample xi, yi, I going from 1 to m. Then we write the matrix. I've already talked about the matrix kxi, kxj. And then we add on the identity m lambda times the identity. Apply that to a vector A equals a vector y. What is y? Y is given from the yi part of the data. So we use the xi part of the data, the input part, in the matrix K, and the output part for the y. So this gives us a well-defined linear system of equations. M by M system of linear equations. You think of this as a linear transformation of the space Rm to Rm. Okay, so this is going to be a non-singular system because lambda is positive. Kij is positive definite. We add on a positive operator to that. We get something which is positive. And so this system is invertible. In other words, we are able to solve that for A, just given the data, and assuming some Mercer kernel, which we added to our structure. Okay, so linear algebra now is, I'd say, the most developed part of computational mathematics. Graduate courses everywhere, applied math, computational math, are just devoted to linear algebra. So the software and the whole development of this computational part of mathematics is the most developed. And so that can be brought to bear for solving this problem under a huge variety of circumstances. Some friends in scientific computation talk about millions of variables here. Another thing about this system is that the matrix K, for the kernels that I've talked about, and for most kernels, all the kernels I've talked about, have the property that they're almost diagonal matrices. The Gaussian kernel is the most easy to see there. As you take x very far from xi, very far from xj, you have this exponential decrease of the kernel function. So the matrix becomes concentrated close to the diagonal. And so what that means in computation is that the linear algebra effort to solve that system is on the order of m, not m cubed. Okay, you have to, and for the case of the polynomial kernel, you have to work just a little bit to see that. The same thing prevails. Okay, well, let me give another example. Maybe I should put this over there. To, well, I can put it over here and not have to erase, I suppose. Huh? Okay. So let me give an example which can be maybe give some of the motivation for these kind of error estimates that I've been talking about. Okay, so this comes from work with I've been doing with Shmuel Weinberger and Partha Niyogi. The main estimates I'm talking about are done with Ding Xuan, Zhou. But we haven't got to the estimates yet. Okay, but we're going to be estimating, as I've talked about a lot, fz minus f rho in some measure. Okay, So I want to talk about an example of learning theory, which is not so far off. This one is motivated more by computational geometry or computer graphics even. So suppose we have a submanifold of Euclidean space, or better, just a surface, say in a three-dimensional space. And the problem in computer graphics is to represent such a surface, find a good representation of that surface. Okay, and so as I say, these considerations work very generally for submanifolds. We want to represent this from data on it, from some finite set of points. Find an efficient representation. At first glance, it doesn't seem to be learning theory, but actually it is. And so what one does is to cover the surface with balls in Euclidean 3 space in this case. For example, we just cut through here by a plane. And now we want to define this part of the surface by a function over this plane, or at least this bounded set in the plane. So what we want to do then is, here's our surface S. So S in this piece, S alpha, here's S alpha would be here. S is the whole surface. S alpha in my picture would be just everything above that plane. This could be thought of as the graph is given by the graph of a function, f from, let's call this x, and the orthogonal to x, this is the real numbers, to r. Thinking of r as the orthogonal to the plane x. And we're working in just this domain in the plane. So x will be contained in our two-dimensional plane I've cut out in R3. Okay? So what we want to do in this problem, modeling surfaces, is to represent the submanifold piece by piece. Generally, we'll have a finite number of these coordinate charts, they're called in topology. I'm just giving an example of how to represent it in one coordinate chart. Okay, so here we have our picture, usual picture then, of a function, and we'll think of that function as a regression function. The function whose graph is S alpha. We'll take that to be the regression function, starting from a little different point of view than that we started with unknown rho. We're going to start with f rho, but we can do that. And now, suppose we have points on the graph. Could be random, say, or taken deliberately, or in many ways. Let's suppose, though, we have a lot of points. They don't have to be exactly on the graph, because this, as learning theory does, deals with noise very well. So here we have the points x1, y1, and so on. They could be generated at random on the surface, if you want. There are many different ways of seeing where we might get these points, but there's a finite set of points on that surface. Okay, any questions about this? As I say, don't hesitate to ask questions. All right, so we have these points on the surface, and now what we can do is apply the algorithm that we've talked about to produce a hypothesis or a function fz in this case, which would approximate this one given by the data. Given by the data that we've seen on the graph. Through optimization, and through, say, optimization using a reproducing kernel Hilbert space. Okay, now if we do that, what do we have? Well, that's where the importance of estimates comes in. So if we have an estimate, Fz minus F rho, if this is small, is that going to help? Well, the problem is the estimate I've talked about is in this integral norm. So this could be small, but this might not even be close relative to the surface, even in the what they call the uniform topology. It may hop around badly. It may have Fz could have very big things like this, peaks and so on. So it would be a very poor representation of the surface. So what I said was the gold standard needs to be modified a little bit. So the answer is, and this comes out of the estimates I did with Ding Xuan, is to put another norm here. In fact, we put the K norm of the Hilbert space. We've talked about the K norm. We've talked about the reproducing kernel Hilbert space. It has a norm derived from K. I wrote the norm down on the basis. It's this norm. We use this norm. And this is surely not the kind of estimates that people have done in learning theory before. It's very far from that. And those estimates that up to this time would never be able to deal with this problem of finding something which approximates this surface in not only the continuous sense, but the differentiable sense. So the idea is that this bounds the norm Fz minus F rho, for example, in the C2 sense. This means first derivative, second derivative. If K just has 4 derivatives. This is the theorem of Ding Xuan. So what we're able to do, if we have estimates like this, then we have estimates like this. So it says that the function we produce becomes close to this with derivatives. So it really replicates the whole differential geometric structure of our surface. So what I want to do is try to convince you that these kind of estimates between the computed function and the regression function directly, instead of these indirect data-driven estimates, these kind of estimates can solve problems that the previous estimates could not. That's the import of what I'm trying to say here. Well, I'm happy to hear any challenges to that or questions. Yes?
What happens when you combine different pieces on the surface?
Okay. Yeah, that's a good question. Well, suppose you have another chart like this to represent this part. Well, the idea is where they overlap, both estimates will be close to the surface itself by our main estimate, so they'll be close to each other. And that allows something called a partition of unity to smooth them all out to get a representation of the whole manifold. Yeah, it's a good question. So, yes?
But this partition still depends on the choice of charts left.
Well, any choice of charts, this will lead to a representation. Sure.
But it's going to depend on the choice of charts.
The representation will. That's right. But even in topology, something I never liked but was always part of the definition of manifolds, that they're defined in terms of charts. And so I resisted that when I was looking at this problem for a long time, but eventually I gave in. And this is the representation. This goes back to the beginning of a differential topology course. I accept it. But, it'd be nice to have something.
No, but even in terms of the performance standard about there,
Yeah.
it's indeed going to depend as well
On the charts?
charts.
Yeah. I mean, we'll see that. Maybe I'll write down some estimates here, and they're nothing too much hidden. But there, of course, the number of charts, the number of things you have to paste together, and so on. Right. Mm-hmm. Yes.
I'm just wondering if this generalization of the ideal spread.
Well, so many things are generalizations of splines. I suppose it could be considered that. I would just as soon not, because this is not exactly polynomial, piecewise polynomial. You could say it's in spirit piecewise polynomial. I'd just as soon not say that. Okay, any other questions on this? Okay. Thanks. Okay, so let me go back then to our estimate. Now, this is the estimate that we have with Ding Xuan. So much of what I say here can be found in many, many papers, including the ones I have on my TTI webpage. So if you do about 5 clicks or so following links, you can find something with my recent papers. And the most recent has a name called Learning Theory Estimates via Integral Operators and Their Approximations. And that has this in it. Actually, we have a whole couple families of estimates, and this is the one that's simplest to explain and carries much of the ideas. So this is not an estimate that I was just speaking of. This is not estimate with derivatives. This is an estimate in the usual L2, the integral error estimate using the marginal measure. And we have here, this is with probability, 1 minus delta. And so this is a pretty simple estimate, actually. The coefficients, no hidden big constants in there, and that's one thing I like. And we see the probability with 1 minus delta. The delta comes in logarithmically, log 4 over delta. And the other term, there's 8, square root of 8. Kappa is the maximum of kxx, square root. K the kernel. Now, kappa one has to think a lot about, but if we take, for example, these kernels, a Gaussian kernel or the Sobolev kernel, if we take the maximum is at x equals t, and that will be simply 1. Or if we put some constant in front, it could be that constant. So kappa is something quite easy to see in most situations. Kappa is something that's very much on the surface, and it represents some kind of complexity measure, but oftentimes, like with a Gaussian, it's just 1 everywhere. Or convolution kernel, simple convolution kernel, kappa is just 1. So that's not too bad. And then we have the rate 1 over n to the 1/4. I would guess that that's the best possible rate for this setting. We can get 1 over n to the 1/3, which is surely the best possible rate, by just making one term there a little more complicated to read. So I sacrificed it a little bit with the rate 1 over m by making this a simple formula. And then f rho is just the k-norm of the regression function. And so maybe the most important invariant here is this k-norm of the regression function. And you should think of that, I like to think of that as something which represents how complex that function is. If you could imagine, go for the moment to a classification problem, suppose you take a large checkerboard, then you have lots and lots of bumps in every direction, and that would give rise to an f rho whose k-norm is quite large. And you'd expect it to be large because it takes a lot of effort to learn that function. Or analytically, in a lot of k-norms I've been discussing, one will get examples by taking something like sine of kx, or sine kxi, using xi, product of that over xi being the coordinate directions in Euclidean space, where k is large. If k is large, then you get all kinds of exponentials. So you can imagine learning a function which is bumpy, all homogeneous bumps in every direction one goes. And that gives very exponential type of learning rates. So that's going to be something that's there or not. The F rho, if it's very hard to learn, that will be represented in that term F rho K norm. Yes?
For 1 over m?
No, I don't think so.
So you have the constant rate.
Close the parentheses. I think close the parentheses look good to me. You say close them?
No, because you have 8. There is a constant, so it will be it will be bounded by a big number. 8 times logarithm 4 over delta.
Yeah, okay. Yeah, so for small m. Oh. You're right. Very good point. Yeah, I've got the parentheses. Should be the other side of 1 over m.
Yes.
Yes, right. Good point. Yes, thanks. Yes. Like this. How's that? Okay, good, thanks. Any other corrections or? Okay. So maybe I should write down an estimate. Yeah, let me write down on the blackboard the estimate we would use for the geometric problem. Just to give us a little solidity. Okay, it's the following. So I'm taking this just from that paper, that very recent paper I finished with Ding Xuan. So it's Fz minus F rho K norm. And remember now, this K norm can dominate the C2 norm, or the C2 distance. So it can be useful for the problem over there for those derivatives we want. Okay, so this is bounded by 4 log 2 over delta, 3 kappa, and now we have to, this is one of these series 2r minus 1, 2r plus 3. So here's r's between, say, 1/2 and 1. 3 kappa. And then we have this term LK minus R F rho 1 over, well, I guess it's hard to read these little letters. 1 over, I think it's, so these exponents are pretty important, so I'll try to get it. 1 plus 2r. Yeah, this is rho 2, 1 over m to the 2r minus 2, 4r plus 2. So that's the way it looks. So this is the important thing here is this K norm is estimated by something rather simple. There is one part here that plays a huge role in our theory, and that is this object. See, R is something between a half, maybe, and 1, with some improvements and modifications, but this is true. And so what is this? R is this index, so you can let this R range. But this is a mysterious part. Now, this replaces the F rho and the K norm. This is a generalization of it. Yes? 2r minus 1 in this place here, 2r minus 2 here. Huh?
R is the
Oh. 2r. Yeah, so this is okay. And this is 2r minus 1 here, maybe, huh? Probably. My glasses, I don't read so well. Okay. Right. Okay. So this is the term which generalizes the k-norm of f rho. And so this is something important because here this family is quite important. So LK is an integral operator defined by the Mercer kernel, which plays a very crucial role in our whole development. So LK is a map from the Hilbert space, HK. Well, it goes from lots of domains, but in particular it goes from HK to HK. Actually, it goes from the space L2 to HK. And it's defined as follows. So the study of this has been crucial in this estimate. LK of f of t is equal to the integral. Here we take the marginal measure, rho x, and we write f of s, k, s, and t, d rho, thinking of this changing with s. So that is this object here, and this is a semi-definite operator, positive, so one can take powers of that and we can invert it, at least if we keep away from the kernel. So all this makes sense, and it gives a lot of a whole family of estimates compared to the first estimate I wrote down. And the proof of these estimates depend a lot on the analysis of this operator. And I do have to mention Italian school, De Vito, Campanetto, Rosasco, which did a lot in bringing that to our attention. LK is an integral operator, and in some sense, it is this data-independent object that gives a picture of the truth in these problems. So this plays a big role, data-independent role. Now, remember the algorithm that I wrote down in terms of reproducing kernel Hilbert space was a linear algebra, finite linear algebra system. Now, in a very rough sense, that system approaches this smooth limit. And that's perhaps certainly one of the key ideas in the proof of these estimates is to see these finite empirical versions of the algorithms and see how they approach in the limit these kind of clean estimates of these clean objects like LK, and to try to estimate that using classic, or by now classic things in the sense of probability theory. So that's one main ingredient in the proof of our theorem. But before that, we can say that it's important to write a decomposition, fz minus f rho. Oops. We want to estimate this, and we use a key triangle inequality to make this estimate. We write this in two parts, fz minus f lambda plus f lambda minus f rho. And lambda eventually will become some function of the data, of the sample size. So lambda will go to 0 as n goes to infinity. So this is the estimate that is basic for our proof of this estimate, this triangle inequality. Now this part depends on the sample. We call this the sample error. And that's analyzed like by the argument I just mentioned. Take the integral operator here and approximate it by the solutions of the equation that I wrote down, which gives you fz. This part comes without any data in it at all. This comes from approximation theory. So approximation theory is used to estimate this.